Okay, there are two methods of working out this problem, and I'm going to show you both methods. Okay, so the first one is easy and short, okay, which is the divergence theorem. Okay, so we want to calculate the rate of flow, that is the flux. Okay, so what do we have here? We have the density, which is 870 kilogram per cubic meter. Okay, and we have velocity, kv is equal to c y squared as x squared k. Okay, and we're given the limits. Okay, so c ranges from 0 to 1, and we have a cylinder, x squared plus y squared equals to 1. Then you know that y is greater than 0. Okay, so we're going to use the divergence. Going to use the divergence theorem. Okay, so the rate of flow, okay, let me just say here, rate of flow is going to be the triple integral, okay, of, let me say this again, let me say it's v. Okay, then we're going to say the density times the divergence of the velocity dv. Okay, so now what you want to find, the divergence of v. Then after that, we're going to do the dot product. We're going to multiply that divergence by the density, and we'll evaluate our limits. Okay, so our what is our vector function? Our vector function, which is v, is equals to c plus y squared plus x squared k. Okay, and what is the divergence? Okay, so the divergence for v is going to be partial x, the y component, which is c, this is the x component, the I component, which is c, plus partial y, the j component, which is y squared, plus partial z, the c component, which is the k component, which is x squared. Okay, so if this means partial, so we're going to differentiate with respect to x. So as it looks here, if we differentiate z with respect to x, is going to be 0, but if we differentiate y, that is going to be plus 2y. By the way, divergence is no unit. Okay, and if you differentiate, you're going to get 0, so that means divergence is 2y. Okay, so we're good. Now it's time for us to evaluate the limits. Okay, so this is where you need to be very careful. Okay, so we have a cylinder here. Okay, it's a cylinder. Okay, so that means we're going to draw a circle. So this is y, this is x. But before I draw a circle, we have a condition here: y is greater than 0. So that means my y is above the x-axis. Okay, so this is what it looks like. Okay, so in this circle is a radius of 2. So yes, 2 is -2. I don't need to draw a full circle because y is greater than 0. So this is my region. Okay, then what is the angle? So I'm going to come from here to here, it's pi upon 2, then from here it's pi. So that means theta ranges from 0 to pi. Okay, then what about r? R, which is the radius. The radius ranges from 0 to 2. Okay, and now it's time for us to compute a triple integral. So rate of flow here is going to be the triple integral. So 2 pi 0 for theta, 2, 0. For R, what about Z? Z ranges from 0 to 1. Okay, then what is the density? The density is 870. What about divergence? For V, that is 2y, and I'm going to say dz, which is minor integral, and I'm going, since I've converted my coordinates to polar coordinates, dy dx is going to be r dr theta. Okay, so now, so this is what you have to know. X equals to r cos theta, y equals to r sin theta, and r squared equals to x squared plus y squared. So that means I can change 2y to polar coordinates. Okay, so this is going to be pi 0, 2, 0, 1, 0, 870. Instead of writing 2y, I'm going to write 2 r sine theta dz r dr d theta. Okay, so this one is like dy dx. And now I'm going to integrate with respect to z. So this is just a constant. There's no z here. So I'm going to just add z. So it's going to be 0, 2, 0, 870 times 2r sine theta z. Then my z limits 1, 0, r dr the theta. Okay, since 870 is a constant, I'm going to pull it out. Okay, and if just say upper bound minus lower bound, you say that you're going to just replace z with 1 and z with 0. And if you replace z with 0, this number is going to become 0. And I'm going to pull my constant, which is the density, 870 pi 0, 2. And if I do my substitution here, upper bound minus lower bound, I'm going to get 2r sine theta r dr theta. Okay, please don't forget this r. Okay, so this is same as 870 pi 0, 2, 0. This r times this r is going to be 2r squared sine theta dr theta. And now I'm going to do my r integration. I'm going to treat theta as constant, so it's going to be 2 pi 0. I'm going to just add 1 to the power of r, which is to then divide by the new power, 2r to the power 3 over 3 sine theta. My limits 2 and 0 to theta. Okay, and if I say upper bound minus lower bound, I'm going to first replace r with 2, then r with 0. And if I replace r with 0, see, this is going to be 0. So it's 870 pi 0. Okay, so 2 to the power 3, that is 8. 8 times 2 is 16. So 16 over 3 sine theta. Okay, then now to theta, I'm going to do my theta integration. So it's going to be 870 16 over 3. Okay, so it's negative cos theta, then the limits pi and 0. Okay, and now I'm going to say lower bound up minus upper bound. Okay, so it's going to be 870 16 over 3 cos 0 cos pi minus 16 over 3 cos 0. Okay, but I already have a negative here, so I'm going to have a negative here, then I have a negative here, so negative plus negative, this is negative minus the negative, so I'm going to get positive. Okay, so I have negative here, so this is negative. Then I'm going to say upper bound minus lower bound, so negative and negative, I'm going to get a positive. Okay, and if you say cos pi, it's -1, so okay, let me write it here. 870 16/3 times cos pi, it's going to be positive 16/3 plus cos 0, it's 1 plus 16/3. Okay, and if you take a calculator, 9280 kilograms per cubic meter. Okay, it's 9280 kilogram per cubic meter. Okay, so this is the first method, and I'm going to show you the second method. Okay, so this is the second method, and I'm just using the flux integral. Okay, so what we need to do, want to compute the double integral of f times ds, and f is given by density times velocity. Okay, in this case our density is just given as a number. In other case, again, it can be given as a vector function, and ds equals to the cross product of ru times rv. Okay, so I'm going to use parametric equations. Okay, and my parametric variables are going to be u is going to be replaced, is going to be presenting the angle. Okay, so the angle here is from 0 to pi. I think from the first method I've shown you why, because this is the upper half of a circle. Then c, since it's independent, I'm going to say z is equals to, I'm going to choose v for z, which ranges from 0 to 1. Okay, I think using parametric equations is very easy and can ease some work here. So if you don't master it, I think you should just go and master it so that you won't have a problem. Okay, so that means this is a circle of radius 4. So I'm going to say my parametric variables. Okay, it's going to u v. So r is going to be x. What is x? Is r cos theta, and r is 2. This radius cos u. Okay, instead of u, I'm writing theta here. I should have written theta, but I've chosen u to replace the angle and v to replace z, plus, so this is plus y is 2 sine u, and what about z is v. Okay, so this is same as ijk. Okay, and now I think it's wise to find ru. Are just differentiating with respect to u, partial differentiating. So if you do partial differentiation here, the integral of cos u is negative, it's 2 sine u, and of sine u is going to -2 cos u, and for v is going to be 0. Okay, then v, okay, as you can see, don't have v here, so if I integrate way to v, I'm going to get 0. I'm going to get 0 here, and I'm going to get 1 here. Okay, and the cross product, okay, so the cross product, which is ds, is going to be ru times rv. Okay, and this is equal. Okay, so this is how to find the cross product I j k, and for ru it's going to be 2 sine u negative cos u, and 0, and here you have 0 0 0. Okay, so to save time, I'm going to leave you. We're going to compute. Okay, so if you compute, you're going to get the answer is going to be 2 cos u I plus 2 sine u j and 0k. Okay. Okay, so that means rate of flow is equal to double integral this region density times f ds. Okay, so f is equals to density times velocity. You know that velocity is zi plus y squared j plus x squared k. So that means f is equals to 870 ci y squared j plus x squared k. And now I want to parameterize f, so it's going to be 870. Okay, for z that is going to be vi y squared, so y is 2 sine u, so it's going to be 4 sine squared u j, and for k that's going to be 4 cos squared u k. Okay, so this is equal to the double integral for density 870. So it's f. Okay, so there's no need for density here, since I said f equals density times velocity. So it's going to be 870 vi 4 sine squared u j plus 4 cos squared u k. They're going to multiply that by ds. Okay, we found ds here using cross product of ru and rv, so it's going to be cos ui plus 2 sine u j. Okay, let me just put 0k to a. So this is now the area of the region. Okay, and if we simplify here, we're going to get, okay, for dA I'm going to choose, instead of writing dy dx, I have u and v. So u is my angle from 0 to pi, and v, which is z, 1 to 0, and that means I'm going to have, if we simplify here, I'm going to get 2v cos u plus 8 sine cubed u dv du. Okay, there's density here. Okay, so it's going to be 870 here. It's going to be 870 pi 0 1 0 2v cos u plus 8 sine cubed u dv du. And there, just what you just did, you just cross product, you just multiply the I component, the I component, the j component, the j component. Unfortunately, you don't have k component here, so it's going to be 0. Okay, and if you compare this integral, you're going to get the same answer we got when we used the first method, 1280 kilogram per cubic meter. Okay, just save time. I'm not going to integrate here, it's going to take me time. So in order to keep this video short, this is the answer I'm going to get. Thank you for watching. I hope for your support in comments, likes, and by subscribing. Thank you.